This will be the first set of notes for Chapter 13, which is about gases. It would help if you have your video notes from your PowerPoint in front of you, but you can write some notes if you don't. So we're going to talk about the combined gas law first, and most books don't do that, unfortunately. As a matter of fact, I don't think I've found one ever that starts with the combined gas law, but it makes some good logical sense to understand pressure, volume, and temperature, how they all relate, and then you could branch off from there and do each of the Charles' law, Gay-Lussac's law, Boyle's law. It's much quicker, and I think you get a better understanding of it. So we're going to use P for pressure, V for volume, T for temperature. I want to tell you that every temperature we deal with mathematically in this chapter is going to be Kelvin. Always convert your Celsius to Kelvin, because that's directly proportional to the kinetic energy involved with these gas problems. Also say that when we hold a volume constant, so like in this PV over T equals P2V2 over T2, if we hold temperature constant, it mathematically is canceled out. And you could see that if you held it constant, it's the same value on both sides. And if we multiply, let's say it was 1 Kelvin, the temperature for instance, if we multiply both sides times 1 Kelvin, we get 1 Kelvin over 1 Kelvin on both sides. It all goes away, because anything over itself is equal to 1, and 1 is the identity in multiplication and division. So remember that if we hold something constant, then we basically don't need to include that variable out of this combined gas law. That's how we branch off and get the other gas laws. So we're going to use a hypodermic as our example, our visual, for you to understand how pressure, volume, and temperature all relate to one another. We'll start out by talking about pressure and volume, if temperature is not considered, if it was held constant. So what happens to the pressure as the volume gets smaller? Well, obviously when you push this in, the volume's smaller, and you could feel that the pressure is high, because when I release it, it pops right back out. The pressure pushed it back out. So pressure and volume are inversely related. When pressure is high, volume is low. It's kind of like the two ends of a seesaw, which are opposite. And you need to be able to understand that when these are side by side, you'll see that when these are side by side, they are inversely proportional. So let's look at another one. Well, what about temperature and pressure? So we're not going to let volume change. We're going to wrap this with duct tape and throw it in the microwave, push the button, and it heats up. Well, when the temperature gets hot or high, what happens to the pressure? Well, obviously, that's why you don't put things in a microwave that are sealed, because it could blow up. Pressure gets higher. Okay? So when the pressure increases, the temperature increases. Well, these are directly proportional. Notice on your ratio that pressure and temperature are one over the other in a ratio form. So when your variables are one over the other in ratio form, they're directly proportional. So if one goes up, the other has to go up to maintain that, that equality. Same thing with volume and temperature. Volume and temperature are directly proportional. If I take off the duct tape, throw this in the microwave, get this hot, well, this volume is going to increase because there's going to get a lot of collisions and a lot of pressure in here. All of this comes from collisions. Collisions cause pressure. And if it's able, collisions can cause the volume to get bigger. Obviously, there's one other. If I were to add gas, the more gas I put in, the bigger the volume. So we could also talk about one other factor on here, and we'll talk about it later, which is the number of moles of gas. Number of moles of gas is directly proportional to pressure and volume too. So let's get this little deal off the screen there. So we will move on. So that's called the combined gas law. Why? It's combined from all the different chemists that did research on these. And remember, it's good science to deal with one variable at a time. So the scientists tried to deal with one thing instead of having all the variables, they would hold something constant and deal with changing one variable. So we start out with Boyle's law, which is just the top of the combined gas law, pressure and volume. Temperature is held constant. Remember, when the factors are side by side, they're inversely related. So if we were to write this up on the board, and if we use, let's say we're going to do P1 V1 equals P2 V2. This is the original pressure and volume. When I change the volume, obviously the pressure changes. That would be the new pressure and volume, which is P2 V2. So when we deal with this, let's just say that we had pressure is 2 atmospheres. We'll use this as 2 atmospheres, and volume we'll use 2 liters. So 2 times 2 equals 4. Well, what if when we decrease the volume, we're going to decrease the volume to 1 liter? Well, to maintain this equality, which it still is the same amount of gas, we have to still have an equality. The pressure would have to be 4 atm. 4 times 1 is 4, 2 times 2 is 4. In other words, when one doubled, the other cut in half. And that's an inverse proportion. So, how would we state Boyle's law? Well, we would say when temperature is held constant, pressure and volume are inversely proportional. There you go. That's Boyle's law, and it's P1 V1 equals P2 V2 as far as an equation. Easy way to remember Boyle's law. When you get upset at something, you're peeved. That may be something that you don't use. I know when I grew up, it was used a lot. When somebody was mad at someone, they say, "I'm peeved at you." Well, peeved is PV, and let's say you're boiling some water in the kitchen, and you get to college, everybody will be cooking macaroni and cheese, and you get sidetracked, and so you hear that noise, and you know, my water's boiling over. So when the water boils over, you're peeved. That's how we remember Boyle's law, because PV, peeve, and boil. So if you find a better way, great, you go for it. So we'll move on. We're going to talk about Charles' law. Charles' law is where pressure is held constant, volume and temperature. So, and volume is over temperature, so they're directly proportional. The way we would state Charles' law would be when pressure held constant, volume is directly proportional to temperature. And, again, a way to remember that, you probably see your little brother and sister watching Charlie Brown, or maybe you watch it. Where do you watch it? You watch it on TV. So Charles' law deals with T and V, and of course it's V over T, and you'll be given the combined gas law, so you can always go back and see, V's always on top and T's on bottom. Remember, temperature Kelvin. So Dalton's and Graham's law, those are both covered in Chapter 12. We are going to deal with them again in this chapter. Just review over those. Dalton's law, of course, the law of partial pressure, that the pressures add up to a total, and the partial pressures of all the gases add up to the total pressure. And, of course, Graham's law deals with effusion or diffusion, and it's rate of the small gas over the rate of the big gas equals the square root of the molecular mass of the big gas over the small gas. So it's kind of a crisscross for small and large gas. We move on, and we're going to talk about the ideal gas law. Well, the ideal gas law here is PV equal nRT. So all we're really doing is we are taking the existing combined gas law, and we're going to add one more factor, which is the amount of gas. So we've got PV over T equals P2 V2 over T2. And one factor that we held constant before in the combined gas law is the amount of the gas. Well, we've got this little cap on top, and the amount of gas stays the same. What if we put more gas in there? Well, then we've got another variable, which is N. It's number of moles. That's what the N stands for, number of moles of gas. So, PV over NT. Now, PV over NT chemists found out right away that no matter what they did with this, it stayed constant. Why? Well, if we double the temperature, either the pressure or the volume or both are going to give a change that's equal to double. So if we double the temperature, pressure doubles. Pressure can't change, so we double the temperature, volume doubles. So when something doubles on top and on bottom, it cancels out. No matter what they did, it always came out to a value that was the same value, and they called this value R. And for atmospheres, and the value is going to be different depending on which pressure unit you use. For atmospheres, it's 0.0821 atmospheres liters over Kelvin moles. So that value is always the value for R. Now, if we deal with a different pressure unit, your notes have all the different types of values that you have for each different pressure unit. It's just like 1 atmosphere and 760 millimeters of mercury are equal in amounts, but the numbers are different because they're different units. So we have different values of R for the different units of pressure. There we go. PV over NT equals R. We generally multiply both sides times NT and get the NT over here. We end up with PV equals nRT. Kind of has a ring to it, and that's the way that we state the ideal gas law. All right, so move on. And we get to, or we don't. Get to Gay-Lussac's law. And Gay-Lussac's law, the next page on the notes, that would be pressure and temperature. The way we say Gay-Lussac's law is that when volume is held constant, pressure and temperature are directly proportional. So that takes us through all of the gas laws. Okay. So we're going to revisit the ideal gas law. I told you that we would have all of the possible values for R. Here they are. You'll have most of these. We're not going to deal with the second and third one, the joule and the calorie, but we will have the value for kilopascal, millimeters of mercury, and ATMs. Those will all be on your possibly useful page. So how do we know which R to use? Look at what pressure unit is in the problem, and that tells you which R to use. What if you're solving for pressure? Well, then you could use pretty much any R you want, and what you get out for the units of pressure are the values, are the unit that is included in your R value. So if it asks for a specific value, well, then you've got to use that R value. So if it asks for atmospheres, then we have to use 0.0821 liter atmosphere over Kelvin mole. So again, that just kind of finishes up with the ideal gas law. We're going to talk about Avogadro's principle, and just to remind you on Avogadro's principle, and we've talked about this before, but this principle states that equal volumes of gas at the same temperature and pressure have equal number of molecules. Well, that's kind of just the opposite of the way we introduced this concept with the mole. So here's our big gas, and here's our little gas. The little gas moves real fast. The big gas moves slow. Because the little gas is moving faster, it takes up the same space as a big gas. Big gas doesn't have to move as fast because it takes up more space already. So what this says is with 1 molecule of each, they take up the same amount of space. Well, if we had 1,000,000 of each, they would take up the same amount of space. If we had a mole of each, they would take up the same amount of space, which is the 22.4 liters that we talk about as our molar volume. So that if we take it backwards, that what we basically said is that if you have an equal number of particles, they take up the same amount of space. Avogadro's principle says at the same temperature and pressure, if you have the same volume, then you have equal number of particles. And you should know that if I ask you to state that principle, you should be able to do that. Just a review from last chapter, standard temperature and pressure. STP is standard temperature and pressure. The conditions are 0 degrees Celsius and 1 atmosphere. And molar volume for all gases is 22.4 liters. Some concepts we've covered in the last 2 chapters that we're going to be dealing with again. So move on. We're going to talk about the other versions of the ideal gas law. Sometimes you're going to be asked to deal with density. And when you have a question or a problem that asks you or asks you to solve for or has density as one of the values, then you're going to have to shuffle the ideal gas law a little bit. How do we do that? Well, we start with PV equals nRT. N, and this is a known fact, a well-known fact, and it will be to you now, is that N equals the mass of something that you have over the molar mass. For instance, helium has a molar mass of 4. If we had 4 grams of it, well, 4 over 4 is 1 mole. What if we had 8 grams? Well, 8 over 4 would be 2 moles. And if we had 12 grams of it, that would be 12 over 4 would be 3 moles. So N equals little m over molar mass, which is big M. So we're going to sub, instead of PV equal nRT, we're going to have PV equals little m over big M RT. Just subbed that value, those variables for N. And then, now we've got a little m, and we need density. What's density? D equals m over V. So we're going to divide both sides by volume, and we end up with m over V, which is density. And we're just going to sub, if you look at the notes, that little symbol is called rho, and that's the symbol we use for density in chemistry and physics. It would be simpler if it was just the D, and we've used the D before, but you need to get used to using this symbol too, because it's very widely used, probably more widely used by professional chemists than the D. So we end up with P equals the density times R over molar mass times the Kelvin temperature. That's just a different version of the ideal gas law that includes density. And that's it. That finishes us up for the first set of notes for Chapter 13. You have lots of practice problems online. If you need more, you can always Google chemistry, gas practice problems, and there's lots and lots of sites out there. But I have some on my website. There's some on the pages that you're supposed to pick up. Work lots of problems, and good luck.